Good morning, good afternoon, and good evening. My name is Natalie Villalobos, and I am a community manager on Google+. Today, I'm really excited to introduce the CERN CMS project, who are physicists working on the frontiers of particle physics. They're doing incredible research on the Higgs boson particle. I'm pleased that Google+ is a platform for intelligent and interesting conversations. And with that, I would like to pass over the floor to Dr. Joe Incandela and Ann Koay, who are joining us from the CMS CERN project and are going to be leading our conversation today.
Hello, everyone. So I am Joe Incandela. I'm head of the CMS experiment at the moment. I am underground. The experiment is behind me. You can see a large red thing there and some green. That's part of the experiment. Later on, maybe I'll move the camera around so you can see a bit more. We're about 30 stories underground, about 300 feet. And right now the detector is running, which is a little unusual when people are here. It's usually there's beam when it's running, but we don't have any beam right now. We're just running the detector. We're detecting particles that are coming in from outer space, basically, and coming down underground. And those particles are called muons, or cosmic muons, and we call them cosmics. And they're very useful to check that the detector is working and to calibrate it and things like that. And in fact, we've been off since November when they stopped the beam. We did many repairs and things like this, and now everything's back together. So we've started up all the detector subsystems, and we're taking cosmic rays right now. So that's the current situation. I could tell you a bit about what we're doing, but maybe it would be good to take your questions. So how do I do that? So there's a question from Kathryn Kure for her 9-year-old. And she asked, how do we accelerate particles to the speed of light? All right, so that's actually fairly simple because we take particles that are charged. You can only really do this with charged particles. And it turns out that with a charged particle, if you put it in an electric field, it'll head toward the positive pole. If it's a positive charged particle, rather, it'll head toward negative charges. So it'll move in the direction of the field, just toward the negative pole. And what we do essentially is we have a big ring. It's actually huge. It's 16 miles around, 27 kilometers around. And that ring has magnets all the way around it. Magnets basically bend the trajectory of the charged particles so they stay on a circular track as they go around. And then at various locations along this big giant circle, we apply these electric fields just at the right time to give the particles a little kick. So they get accelerated each time they go past one of these things. Those are called radio frequency resonance cavities, RF cavities. You don't need to know that. But they basically give the particles a little kick, and they're timed perfectly, so that when the particle comes through, it gives them the kick in the right direction, not the wrong direction. And then you have to strengthen all the other magnets all the way around the ring so that they can handle the particle now that it's going a little bit faster. It's kind of like a racetrack where you have a banked sides, and as we increase the strength of the magnets, it's like we're raising the banks. So we keep sending the particles around, they keep getting kicked, they keep going faster, they go faster and faster and faster, and they get closer and closer to the speed of light. But it turns out, as you get close to the speed of light, there's a huge amount of energy that's required. Particles get very heavy, and it gets harder and harder to push them. So at a certain point we stop, but it's very, very close to the speed of light, not quite. Okay, hopefully that answers your question.
So why are the particles heavier when they get closer to the speed of light?
It's an interesting thing. It turns out that particles, if you like, I'll just mess around here a second. If you like, according to the theory of relativity of Einstein, okay, nothing can go faster than the speed of light. And the only thing that can go the speed of light is particles with no mass at all. And part of the way that rule is enforced is that you have to pump more and more energy into particles to get them to higher and higher densities. And it turns out that going from, say, 0.99999 times the speed of light, adding one more 9 is a huge amount of energy, but you barely change the speed at all. So particles become massive just because energy is equal to mass times the speed of light squared. E equals mc squared. So as you pump more energy into them, they're effectively more massive. I don't know if that's answering your question to your satisfaction, but special relativity is a little bit tricky, and it's very hard to make it very simple. It's just the rules of the game. All right, so I have another question, or should I take questions? Are there any more questions out there?
Oh, I was wondering, would you mind explaining the mechanism by which the products of collisions are detected?
I can see your mouth moving, but you're muted, I think.
Sorry, can you hear me now?
I'm sorry, you were not muted. Try again.
Would you be able to explain the mechanism by which the products of collisions are detected?
Explain the mechanism by which the
Products of collisions are detected, the collision products.
Well, how the collision products are detected? Yes, we use very simple techniques that have been developed over many, many years. There are a couple of ways we do it still. Many of the old methods are no longer used. But one of the nicest ways we do it is essentially we use the fact that particles, charged particles, for example, when they pass through materials, they ionize those materials. They knock electrons out of their atoms. And we can apply an electric field and collect those electrons and get a little signal. So we use silicon wafers for that purpose. Or sometimes we use gas. A gas with wires in it can be used in the same way. The charged particle passes through it, it ionizes the gas molecules. If you are applying an electric field, some ions move in one direction, some move in the other direction, and we collect the ions on little wires, and the wires pulse a little signal, and then we know where the wire is, so then we knew where the particle passed, things like this. There are other ways we do it as well. Sometimes we use plastic, and if the particle interacts with plastic, it showers and produces lots of light. And we can collect the light and use a photo detector to detect the light. The trick is not so much to detect the particles, it's to detect them very fast with many, many channels and try to make a photograph, if you like, a three-dimensional picture of the whole interaction. So over about 100 years of us learning how to do these things, take it about 100 years, we've developed ways to build detectors like we have now that can take basically a picture every 25 billionth of a second. And that picture can have 100 million pixels, if you like, and it's three-dimensional. And we can actually reconstruct that whole thing and decide whether we like it or not and keep it or not. But that's a longer story to explain how that's synchronized and so forth.
Okay, so how does the LHC affect the power grid for Geneva and the surrounding population?
Well, if I'm not mistaken, most of our power comes from France, not from Switzerland. So it doesn't affect Geneva too much. We don't use that much power in some sense. We do use a fair amount. I can't remember the number exactly, but it's smaller than a nuclear power plant, that's for sure. It's a fairly, you know the numbers offhand? I think it's 150 megawatts. It's a fair amount, it's true, but it's not like a city. In one way, we save a lot of money, actually. We save a lot of power by having magnets that are superconducting. Okay? What's nice about a superconducting magnet is that once you established it with a current, once you put a current into the superconducting magnet, it just stays there. You don't have to add any more charge, any more power. So we can save a lot of money. And the whole accelerator is superconducting in this sense. Almost all of it is superconducting. Now the problem is, to keep it superconducting, you have to keep it very cold. So you have to actually run a lot of refrigeration. So we're the biggest cryogenic plant in the world, the biggest freezer, if you like, in the world. It's the biggest, very biggest liquid helium user in the world. So we have liquid helium in order to get the magnets down to 2 degrees above absolute zero. That's about minus 271 degrees Celsius, or probably much more like 400 degrees below zero Fahrenheit. They're very, very cold, and to keep them cold, that takes some power. But we still save a lot compared to if we used normal wire magnets where the power would be dissipated in heat. Okay. Does that answer your question?
Yes, it does. I have one more.
Sure.
What are the long-term plans for the LHC after the existence of the Higgs boson is proven or disproven?
That's a great question. Many people think the Higgs is our big, big thing, and it is a big thing. We're very excited about possibly finding the Higgs. But it turns out that the Higgs is really like the first step toward potentially a whole new realm of physics, of new insights. We theoretically came up with the idea of the Higgs to explain why particles have mass. And you probably have heard this. And it looks like the whole concept works very well because our theoretical equations, our models work extremely well in explaining things, once you include the Higgs. But the Higgs turns out to be a very special and very peculiar particle. It's kind of amorphous. It has no spin. It has no real characteristics like other particles. Other particles have spin a half or spin one. The photon has a spin one. It's a vector particle. It has a direction associated with it. Electrons have spin a half. Spin a half particles are very important because they can be built into structure. The Higgs is spin zero, which is really strange for a fundamental particle. And it turns out that theoretically, this is really bad. It creates lots of problems. And to fix the problems that are associated with the Higgs, we believe there has to be a whole new something. Now what that something is uncertain. It could be a whole new spectrum of particles, like what we call supersymmetric particles. It could alternatively be additional dimensions of space. So the Higgs is kind of like, if you like, the gatekeeper to a whole new realm of discovery, we hope. So while we're looking for the Higgs, we also have dozens of different studies that are underway for these other things. In fact, we have hundreds of people working on things that aren't associated with the Higgs. So we'll continue. But once we discover the Higgs, I should also say we'll spend a lot of time getting a lot more data in order to study the Higgs itself and understand its properties. Because the Higgs, there's not just one possibility for what the Higgs is. There are many different possible theories that have Higgs in them, have different characteristics. So understanding the details about the Higgs actually points us in these other directions, help guide us in the new realms, the frontiers of knowledge.
Wow, that's fascinating. So could actually be another phase of matter?
It could be a whole new, almost like another universal, well, it's like another image of our existing matter, but slightly different. All the particles could have partners that are just much more massive, and in all cases slightly different in their properties. And this would be extremely important to know because it would tell us a lot about the basic structure of the universe. These particles that we're trying to find are not things you find in everyday life, but it turns out that they're kind of like our genetic code, the genetic code of the universe. Once we know what they are and how they behave, we understand actually what the universe is in a very, very fundamental way, maybe how it was structured in the very beginning and so forth. So it's very, very important for us to try to find the Higgs and then find out what other things there must be that help solve the problems that are raised as a result of the existence of the Higgs, okay? So we have a lot to do. We'll have a lot of work for many years to come. And these two young little boys that I see, they could easily come and work at the LHC someday when they're older because we have plenty of years ahead research. I may be retired by then. I've been working on this stuff for 25 years. But there's lots still to go.
My 8-year-old is impatient with a question.
Yes.
Connell?
So why do you do it underground? Why can't you just do it on the surface?
Ah, that's a good question.
That's a good question.
Want to know why we can't do this on the surface? Remember I told you that we're sitting here right now running the detector but without the beams on, and we're looking at particles coming in from outer space. Well, those particles, actually, many of them make it down here, but most of them don't. So the ground actually shields us from cosmic rays coming in from outer space. People don't realize this, but there are particles zipping through you all the time coming in from outer space. Those particles can make a lot of unnecessary noise in our experiment. Now, there's other reasons as well, though, that are probably more important. We want the accelerator. The accelerator is amazing, okay? The accelerator is probably one of the wonders of all time, because this is a machine, you have to remember, that's 26 kilometers around, right? 26 kilometers is big. That's more than half a marathon. And yet, it focuses beams to collide inside of our experiment. It focuses them down to a diameter that's smaller than a human hair, about 1/10 the size of a human hair. So imagine the precision that this machine has to have. Okay, 10,000th of an inch is roughly the kind of precision you need, or 1,000th of an inch, all the way around. This is unbelievable precision. How do you retain that precision over time? Well, you better build this thing in good rock, in a very solid area. So we have to go down to where there's bedrock, where the whole accelerator can be built in a very, very stable regime. You can't build it on just soil. It'll sink. It'll sink differently in different places. You'll have constant headaches. So that was a very good question. In fact, I've never really thought about it in detail, so I thank you for that. Any other questions?
So I was wondering if the school, it says Festus, if they had a question. Looks like they're looking for a question. Do you guys have anything?
Okay, my name is Frank. I want to know, I'm speaking from Ghana. I want to know, late last year, there were some neutrinos which were found to be traveling faster than the speed of light. Now, in that case, won't it kind of disprove Einstein's theory of relativity, and what implications for physics in general?
Yeah, there was an experiment, and not our experiment. CERN does many different kinds of experiments. And one of the experiments it does is to send neutrino beams from here about 1,000 kilometers to a detector in Italy. And those were to study various properties of neutrinos. Neutrinos are fascinating things. They're particles that are very, 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 very light. In fact, the sun produces billions of them, and those are flying through you all the time. You have thousands of them passing through every square centimeter of your skin every second. But they don't interact. They're very, very weakly interacting, so they don't bother you. Now, if you produce very strong ones, which is what they try to do at CERN, and they direct them to this detector, it turns out they do funny things, they do interesting things. They can change types as they travel. They can change from one type of neutrino to another. They have a small amount of mass. They're very strange particles, and we're trying to understand them better for the same reasons as we're trying to understand the Higgs. And it turned out that one of the experiments found that they seem to get there faster than they should, faster than the speed of light, by a very small amount, 60 billionths of a second faster over 1,000 kilometers. So that's not so much faster, but it's a little bit. Now, they've been trying to understand this. I should tell you that most scientists are very, very skeptical. Most of us believe that there's something that's just not understood, and that probably they're going to find that they're not going faster than the speed of light. And in fact, there are many other experiments that are going to be run to try to understand that and check that. So all of us are sort of waiting to see what the other experiments find, because maybe this one experiment is wrong. And you have to realize that what we do is really difficult in general, and that's why we have multiple experiments to check each other. So my experiment behind here that you see is the CMS experiment. There's another big experiment called
Uh-oh.
Uh-oh. It looks like our scientist might be on pause.
Okay.
Because he's frozen. Darn.
Well, he did say it was like the biggest refrigerator in the world, right?
Oh.
So what sometimes happens in Hangouts and with internet is that sometimes people drop out. But we're in communication with the people at CERN, and so even if they do drop out, they know to jump back in. But I just want to say that I think you guys all asked really great questions. I'm learning a lot from your curiosity.
Well, I was thinking about asking them about antimatter and the Alpha project.
Yeah, I mean, I think the next question we'll probably take is one from the Google Plus stream. They'll jump back in, take a question from folks who can't get in the Hangout with us. And then that'll probably be our last question. And then I think we're going to actually start a second Hangout for more schools to join, more people to join, so that, it's pretty rare that anyone gets to hang out with scientists, what would they say, like 30 stories on the ground.
Yeah, this is a great opportunity. I can't believe it.
Yeah, I think it's really amazing when he was just talking about how things really have to be calibrated and everything has to be so exact. I was actually wondering if things get, kind of off kilter, how do they recalibrate that machine, or do they ever?
I heard that they do. Is that where they exploded after several months ago?
Oh, here they go. Yay, they joined!
Hello, welcome back.
Welcome back, welcome back.
I think we were hit by a cosmic ray.
Yeah, well, what we were saying is, Dr. Joe, was that you guys said you guys were the biggest freezer, and what ended up happening is when you guys dropped out, you froze for a second in time.
Yeah, I see. Anyway, I think I was answering the question, but it's true. If it turns out that other experiments do the same thing, then it's a big deal, and Einstein could have been wrong by a little bit, and we'll have to figure out what's going on with these neutrinos. Like I said, most of us, to be honest, are very doubtful that this result will stand, or at least very skeptical. Any other questions?
Yeah, so we actually have, we're going to take our last question. I believe it's from the Google Plus stream. It's from Zoran Moretic. What amount of data do you need for a conclusion?
Well, it depends what conclusion. But if you like, probably, if you're asking about the Higgs, for the Higgs particle, for the Higgs boson, we need about 4 times as much data as we already have. To give you an idea how much that data is, it would correspond to about 1 million billion collisions, proton-proton collisions. And so, so that's a lot. And
yeah, it sounds like you guys have a lot of work to do.
Yep. Who else should I give their time? Has everyone spoken? I think everyone has spoken.
Yep, everyone's been able to ask a question. So I think this is a great opportunity to actually wrap up, say thank you to everyone at CMS and CERN. We're going to start a second Hangout for a new group of folks. But thank you, everyone, for joining.
Thank you so much for hosting.
Yeah, it was great. Thank you for your questions. They were excellent.
Very good question. Yeah, we'll be back in just 3 minutes. So be sure to tune in just a bit. Bye.
Hey, thank you for having me.